Hey guys, welcome to another session on math and statistics for data sciences. So in our previous session, we introduced the measures of central tendency, where we covered five kinds of measures, and these basically measures gives you an indication of typical value of a particular variable, or the central value, or the expected or average value for a particular variable. Now we looked at how we can compute these different metrics for any set of data. So for example, for the first metric, which is the mean or arithmetic mean, we compute the mean as the ratio of the sum of all values of the variables. So we just add 2, 3, 10, 5 and 20 here, which comes out to 40. We divide by the total number of values, which is 5, and we get the mean value as 8. So this is how we compute the first metric here. Now, the problem with mean value was that if there is an extreme outlier value, for example, if instead of 20, this value is 200, the sum would have become 180 more, which would be 220 divided by 5. And in that case, the average would come out to be 44, or the mean would come out to be 44, which would not really represent a typical value in this set of values, because the typical value, 4 of the values are way lower than 44, and therefore to basically tackle this particular disadvantage of mean, we use something called a median, and the median is computed as the middle value of the distribution when all the values are arranged in a ascending order. So for example, if we sort the values given above 2, 3, 10, 5, 20, we get 2, 3, 5, 10, 20, and the middle value comes out to be 5, and 5 is the median value here. Now, even if we would have 200 instead of 20 here, the median would have still remained 5, because 200 would have been still the fifth value in the sorted distribution. Now, these two metrics were good for numerical kind of variables, and if you remember, there are ratio level and interval level variables, which are the numerical variables. So the mean and median could be computed for these kind of variables, but what if we have a categorical variable like color? So color is a nominal level variable which does not even have an order to their values. We cannot say that blue is greater than red and so on. So in that case, we use the mode as the measure of central tendency. So what we do is we count each of the colors in the total distribution, and we see that the number of blue colors were 3, red were 3, green 2, yellow 4 and black 3. And then we simply select the color with the greatest frequency, which comes out to be 4 in this particular case. Now there could be a case when let us say instead of this 3 we have a 4, and therefore now there are two colors actually which have a frequency of 4 and which is also the highest frequency. So in these cases we actually have got two mode values for this kind of a variable. So we have both yellow and black as the mode values, and these are also called bimodal distributions. So there can always be more than one mode, 2, 3 and so on, given that all the frequencies should be equal for the highest frequency color. So there can be even 3 colors with the same frequency of 4, and in that case there will be 3 modes for this particular distribution. Now next we looked at some of the application based metrics. So we looked at something called a geometric mean, for which we normally use this for calculating the compounded mean return over many years of a investment. So what we if you remember, we looked at a return of 10% in the first year, 5% in the second year. So this was first year return, this was second year return, and then to calculate the geometric mean return, what we did was we simply added 1 plus 0.1, 1 plus 0.05, and we did the square root for this particular value to get the final mean return, and we subtract this by 1. So what we are essentially doing here is 1 plus r. So this is, let us say, this is the geometric mean. We are doing the square and we are doing 1 plus r1, 1 plus r2. So from this expression, we are actually getting to this particular expression here. Now this 2 represents the n, which is number of years in this case. Now let us say instead of 2 years, we have 4 years. So this will be 1 plus r1, 1 plus r2, 1 plus r3, 1 plus R4. Now since this total return is computed over a 4-year period, this should be equal to 1 plus geometric mean raised to power 4, since we are calculating the geometric mean for 4-year period here, and therefore the geometric mean in this case comes out to be, so let us use this particular symbol pi. So this is normally used for product of expression. So for example, if you do pi xi, this is nothing but equal to x1 multiplied by x2, x3 and so on till xn, whatever numbers are there. So we are simply using pi operator to show the multiplication operator. So this is 1 plus ri, where I could be equal to 1 till 4, since there are 4 terms here, and we are raising it to 1 upon 4, and finally we are subtracting the 1 here. So this will give you the geometric mean return over the 4-year period. And if someone wants to generalize it for a n-year period, we simply can use from I equal to 1 till n 1 plus ri raised to power 1 upon n minus 1. So this will give you the geometric mean return over a n-year period. So this is how we calculate the geometric mean. Similarly, to calculate the average velocity when equal distances are covered, so we saw that there was a distance covered with a velocity of v1 or a speed of v1, then distance covered d with a speed of v2, and we computed the harmonic mean value as 2 v1 v2 upon v1 plus v2. So this was the average speed which we got for the total journey for both the distances. Now let us say if we have more than 2 terms. Now one thing to note here is this can actually be written as 2 upon 1 upon v1 plus 1 upon v2. So these two are similar terms here. Now let us say we have to again generalize this for n terms. So what we do, instead of 2 we make the numerator as n, and once again, since we are summing in this case, instead of doing a product, what we do, we use the summation, and we have I equal to 1 till I equal to n and 1 upon vi. So this can be a general formula for the harmonic mean as well. So one does not really need to remember these formulas, but just need to understand how we are coming up with these formulas, so that if there are certain terms given, one can easily compute the harmonic mean. So one can even remember this one actually, and just derive this one using the n equal to 2 equal case here. So this is how we calculate the geometric mean and the harmonic mean. Now what we'll be doing is from measures of central tendency, we would be moving to measures of variation or measures of dispersion. So what these are this gives us an indication of, it tells us how much variation is there in data, and generally it is given with respect to the central value, which was actually the one of the measure of central tendency, and that could be both mean or median or any other value in general. So the measure of variation or measure of dispersion is a measure of how the variable is spread, or a measure of how much variation is there in this particular variable with respect to the central value. Now once again, we'll be looking at a lot of such measures here. So the first one is an easy one, which is called the range of a distribution. Now let us say we have a example data here, 5, 8, 12, 20 and 25. So I took a simple example. Range is computed as max minus min, which is 25 minus 5, which is 20. So this gives you a range of a particular distribution, the difference between the maximum and the minimum values of the data. Now once again, the problem here is, now just like we had in the arithmetic mean, let us say this particular value, instead of 25, it's an outlier, and let us say this is 500. Then for that particular case, the range would be computed as 500 minus 5, which is 495. So although 495 represents the true range for this new data set, where there is an outlier with 500 value, this does not really give us a typical range of the data, because most of the values are still in the range of from 5 to 20, which is a very small range of 15 actually. So comparing 15 with 495 doesn't make sense, and therefore range is again, so range is sensitive to outliers. Just like the arithmetic mean was sensitive to outliers, the range is also sensitive to outliers. So this is about the range of a distribution. The next metric, which is one of the most common metric used in most of the financial applications as well, is called the variance of the distribution. And this is computed as, so there are two kinds of variances which we will be looking at. One is population variance, which is represented by sigma square, and then there is sample variance, which is represented by small s square. And there is a slight difference between the formulas for the two. So population variance is computed for the whole population, and sample variance is computed for the sample. So the difference between population and sample we'll be looking in more detail in the next two sessions, but right now I can tell you, like, the population is nothing but the set of everything which we have. Let's say we want to study a particular age distribution for a particular standard in a school. So there are various sections in that standard. Let us say there are 8 sections. So there are 8 sections. So this is the whole population in that standard. We are trying to check the age distribution. Now, instead of taking 8 sections, that is all the sections in that standard, what we do is we simply pick a small part of this whole population, which is called the sample. And instead of looking at all the sections, we simply look at one of the section. So this is a sample and we are looking at one of the section. So when we do that, this particular small part of the population is called a sample, and we make certain conclusions from this sample, based on which we can conclude with certain confidence about those particular metrics for the whole population as well. So we use the sample to make certain conclusions which can then be generalized for the whole population based on a certain confidence level. So even if you don't get what I'm saying right now, we'll study it in more detail in the coming sessions. But in general, this is how we differentiate between a population and a sample. Now, a population variance is computed as sigma square is computed as the summation of xi minus x bar whole square upon the population size. So the population size is denoted by the capital N letter, and then the sample variance is computed as summation of xi minus x bar whole square divided by small n minus 1. This is the sample size, and this was the population size. So we denote the population size by capital N, while we denote the sample size by small n. Now xi in this case is each value in the sample, while x bar is the sample mean of the whole data. Now we'll again look at one of a simple example here. So let's say we look at the same example which we had earlier for range. So 5, 8, 12, 20 and 50. Now to calculate the variance, and we first need to compute the sample mean, which is computed as summation of all values divided by n. So 5 plus 8 13 plus 12 25 plus 20 45 plus 15, which comes out to be 60, and we have, so 5 13 25 45 50 60. So let's keep this value actually as 25 here, so that we get the sum as 70 divided by 5, and this comes out to be 14. So this is the mean value here. Now to calculate the variance, what we do is we calculate 5 minus 14. So basically we are doing xi minus x bar whole square, 5 minus 14 whole square, which comes out to be 81. Then we have 8 minus 14 whole square, which is 6 square, which is 36. Then we have 12 minus 14 whole square, which is 2 square equal to 4. 20 minus 14 whole square, which is 36 again. And finally 25 minus 14 square is 11 square, which is 121. Now we simply add these all values and this comes out to be 278. Now to calculate the population variance, we know that it is the summation of xi minus x bar whole square upon capital N. So the population size here is 5, and let us assume right now that this is the population. So we know that N is equal to 5 here. So this comes out to be 278 divided by 5, which comes out to be 555.6. So this is the population variance for this particular distribution. Now just like we computed the population variance, now this time we assume again, let's say we have the same data 5, 8, 12, 20 and 25, but this time we assume that this the sample instead of population, and the sample size in this case is 5. So we calculate the sample variance now for the same data as 278 divided by n minus 1, which is 5 minus 1. So 278 by 4, which comes out to be 69.5. So since we are dividing here by n minus 1 instead of n, the sample variance is always higher than the population variance, because the denominator is lower in case of sample variance. Now this is how we calculate the variances, both the population variance and sample variance of a distribution or a data. Now just like we had a range which was sensitive to outliers, even the variance is sensitive to outliers. This is because we are giving equal weightage, again equal weightage to each of the values in the numerator, which is basically the same issue which we had with the arithmetic mean as well. Since we are adding the values for each of these 5 values in the data, we are giving it equal weightage. So whenever there is an outlier, let's say if there was an outlier here 200, then 200 minus 14 would have become a very huge value, which would have biased the variance on the upper side. Therefore even the variance is sensitive to outliers. Now one of the disadvantage of variance, so this was the second metric which we looked at. So one of the disadvantage here is it is sensitive to outliers. Another disadvantage is the units of variance is not same as the raw data, because since we are finding the squares in the numerator, so let us say if the values which we had earlier, so this raw data which was 5, 8, 12, so 5, let us say we have the raw data 5, 8, 12, 20, 25, and let us say we are measuring speed, so all these values are meter per second. Then what happens is that the unit of variance is actually meter per second square, since we are doing an xi minus x bar whole square to calculate the variance, and therefore the units for variance becomes square of the original raw values, and therefore the variance in its value form is very difficult to interpret, because one cannot say whether the variance is high or low, because the variance value itself is not in the same units as the raw data itself. So to counter this, what we do is we use the third metric, which is called the standard deviation, which is again a very common used metric to calculate the variation in the data, and it is computed as the square root of variance to bring it back in the same units. So once again, let us say if we had a sample variance, let us say of 69.5, then this was sample variance, so this is s square if you remember. Now if we have to calculate the sample standard deviation, it is computed as the square root of sample variance, which comes out to be 8.34. So this is how we calculate the sample standard deviation, and similarly the square root of population variance can be done to calculate the population standard deviation. So the advantage here is over variance is that the values here are in the same units. So values here are in the same unit as the raw data. So this is one of the bigger advantage here. And once again, standard deviation is one of the most used metric for calculating the variation in data. Now, till now, all the three metrics which we have looked at, range, variance, and standard deviation, all three of them are actually sensitive to the outliers for their own reason. And therefore, to counter the outlier thing, what we do is we use this fourth metric, which we have actually looked before as well. It is called the interquartile range of the data. So interquartile range, as we looked at earlier, is calculated as the difference between the third and the first quartile of the data. And third quartile data and first quartile data are nothing but they are defined as 75th percentile data and 25th percentile data respectively, which means that 25% of values in data are lower than Q1, and similarly 75% of the values are lower than Q3. So this is how we calculate the 75th and 25th percentile of the data. Now let us say we were able to calculate the 25th and 75th percentile of the data when we had continuous distributions like an exponential distribution. We derived it, if you guys remember, in our distributions. We did it using integrals. But now what if, let us say, we have something called a discrete data, which we have been looking in these sessions. So let us say once again the same example. So 5, 8, 12, 20 and 25. So how do we calculate a particular percentile value for this kind of a data? So what we do is, so this is once again a standard rule to calculate the any percentile of the data whenever we have a discrete set of data. So we have n equal to 5 values here. There are 5 values here. Now pth percentile data point is given as the p into n plus 1th data point of the data set. So once again, let us say we want to calculate Q1 here, which is the 25th percentile data, and therefore p is 0.25, n plus 1 is 6, therefore 0.25 into 6, which is nothing but 1.5 fifth value would be the first quartile data in this particular distribution. Now how do we calculate the 1.5th percentile? We know that the first value a1 is equal to 5. We know the second value a2 is equal to 8. Therefore, to calculate the 1.5th value, we simply use interpolation between these two values, and therefore we calculate the value as 5 plus 0.5 times the difference between the second and the first value, and this comes out to be 6.5. So we get the first quartile data point here as 6.5. Now to calculate the third quartile point, we know that p is equal to 0.75, and once again n plus 1 is equal to 6. Therefore p into n plus 1 is 4.5. Now what we do for 4.5th value is we interpolate between the fourth and the fifth value, which means between 20 and 25, and therefore Q3 value is calculated as 20 plus 0.5 into 25 minus 20, which comes out to be 22.5. So this is how we calculate the third quartile point of the distribution. Now, since we have done this, now we can easily calculate the IQR as Q3 minus Q1, which is 22.5 minus 6.5, and this comes out to be 60. So this is the interquartile range of the given discrete set of values. So this is how we calculate the interquartile range of the discrete set of values. Now, one thing to note here is since we introduced interquartile range as a metric which was supposed to counter the disadvantage of the first three metrics, that they are sensitive to outliers, we'll see now how the interquartile range is actually not sensitive to outliers. So even if there are outliers, the IQR value will not be affected by those outliers. IQR value would still remain constant, just like we saw in the case of median, that the middle value was not really affected by the outliers. Similarly, in this case, we'll see how interquartile range is not affected by the outliers as well. So to do that, we'll use an illustration here, which is called a box plot for a particular distribution. So this is once again a very useful plot or a visualization tool for a data which normally has some outliers. So what we do, we call this a box plot. This is also called a box and whisker plot. So why is that? Because this particular middle part here is called the box, and this branch like thing is called the whisker, and therefore this is called a box and whisker plot. Now, how do we really make this kind of a plot for a given distribution? Now, once again, we'll take our standard example, which we have been looking here, 5, 8, and then we had 12, 20, and 25. Now, there is something called, so this is again very important for making a box plot. It's called a 5-number summary of a distribution. So what is a 5-number summary? 5-number summary will help you make a box plot, and it also gives you a summary of distribution of different points in the data. How do we calculate it? We have to calculate 5 values basically for this distribution, and these values are minimum value, the first quartile value, the median value, which is also the second quartile value, because 50% of the values are less than the median, which is the definition of second quartile, then the third quartile value, and then the max value. Now the minimum value clearly is 5. The first quartile value, which we calculated in our previous slide here, was 6.5. The median value is the middle value, which is clearly 12 in this case, and the third quartile value we calculated as 22.5, and then the max value is 25. So this 5-number summary will now help us make this box plot. So for the box plot, if you look at the plot here, what we do, we first draw the box, and the upper and the lower range, lower limit for the box is given as the third quartile and the first quartile value of the given distribution, which in this case would be 6.5 and 22.5. Now, since the limits for the box are 6.5 and 22.5, and these are the first and the third quartile values, therefore IQR, which is nothing but computed as Q3 minus Q1, is calculated as the length of the box itself, which comes out to be 16, like we calculated in the previous slide. Now there is a central line here which represents the median of the distribution, and this need not be at the centermost point of the box. This can be anywhere in the box, but in this case, since the value is 12, it is closer to the midpoint of the box. But note that median could even be here or anywhere else in the box as well. Now to draw the whiskers, what we do, we use something called a Tukey criteria, which again we have seen before. So to determine the length of the whiskers on both the sides, we use this Tukey criteria. Now if you remember, according to the Tukey criteria, a value is an outlier if the value is less than Q1 minus 1.5 times the IQR. So if you remember, we did calculate these values for an exponential distribution earlier while we were looking at continuous distribution. And from the upper side, if it is greater than Q3 plus 1.5 times IQR. So in this particular case, let us call this lower limit and this as upper limit. So in this particular case, if we calculate these values, the lower limit comes out to be 6.5 minus 1.5 times the IQR. So IQR is 16. So 1.5 times 16 is 24, and 6.5 minus 24 is minus 17.5. So the lower limit here could be called as minus 17.5. So this is the lower limit here. Similarly, the upper limit calculated as Q3 plus 1.5 times 16, which is again 24. So 24 plus 22.5 is 46.5. So this is the upper limit to the box plot, and we can put the value here as 46.5. So this is how we calculate the different values which you can see here in the box plot, and this helps us to make this particular box and whiskers in the plot. Now there's one thing which is remaining, which are these small circles here, and these are nothing but outliers in the distribution. Now these circles could be both below the lower whisker as well as above the upper whisker, but in this particular example they have shown certain outliers below the below the lower whisker, although there are no outliers in this particular distribution, because we know that in this particular distribution there are no values less than minus 17.5. But for just to explain like what these circles represent, there could be outliers in the distribution which are nothing but which are values less than Q1 minus 1.5 times IQR. Now this is how we get the box plot. Now to our initial point, how the IQR or the interquartile range is actually not sensitive to the outliers. One can imagine that even if we have outliers here, let's say above the upper whisker, or we have it on the below here or below the lower whisker, you can see that IQR still remains equal to the length of the box only, and therefore it is not affected by the outliers at all. So this is very similar concept to how we were looking at the median, where the median was not really affected by the outliers since it was the middle value. So whenever you add a lower or a very high value, it will not affect the median because it remains the middle value. And this is how both median as a measure of central tendency and IQR as a measure of variation or variance is not really affected by outliers. So this is one of the advantage of this fourth metric of dispersion, interquartile range, that there is no sensitivity to the outliers, and therefore whenever there are outliers, one should stick with using IQR to calculate the measure of dispersion. So this is it. From this particular session, we looked at mainly four metrics for variation, and these will be again used in various application in data sciences.